So if you guys have followed my channel for a while, you probably know I make a lot of videos about networking. And often when I make these videos, there are some fundamental misunderstandings I see in the comments section, specifically around layer 2, the link layer. So today I am digging deep into the technology at layer 2, the link layer. Why do we call it bridging instead of routing? What is an Ethernet 2 frame or an Ether type? And what is spanning tree used for? If those are questions that you can't answer, come along on this adventure. Quick primer before we get started. It's kind of important that you're aware of the OSI model, or the TCP/IP model that you might have heard of. So over there I've listed all the different layers that OSI has, 1 through 7. As network engineers, usually we talk about 1 through 4 and then 7. We don't really care about 5 and 6, and a lot of people don't either. So today we're specifically talking about layer 2, the link layer. So in this case, layer 1, the physical layer, would be either wired Ethernet, I guess it could be optical as well, or Wi-Fi. They're both fairly similar. Layer 2 is the MAC layer, the link layer. Layer 3 is where we have IP, the Internet Protocol. And layer 4 is where we have TCP, UDP, those sort of protocols. So TCP and UDP and even IP are too high level for this talk. It's just going to be about MAC addresses and the link layer. In the link layer, we talk about everything as a MAC address. A MAC address is often called the physical address, the hardware address, because usually it's assigned to the network card when the device leaves the factory. And so every network card should have a physical MAC address assigned by its vendor, and the address is 48 bits long, that's 6 bytes, looks something like that. The first half of that MAC address identifies the OUI, or the organization who produced that hardware, and the last 3 digits are random or sequential. Take a look at that MAC address now, because we're going to be using MAC addresses a whole lot in this video. So before I can talk about modern Ethernet, I think a bit of a history lesson is in order. Back in the late 1960s, a number of different research groups were trying to figure out how to connect computers together. Now the biggest one of these projects was ARPANET, managed by ARPA, the U.S. Advanced Research Projects Agency, who was in charge of spending defense money to try to foster technological development. So ARPANET built a network of universities, government institutions, and very large companies like research labs, and they were trying to network computers at each of these facilities in a sort of mesh. So at each facility they would have a router, they called it the IMP, the Interface Message Processor. The IMPs were all connected to each other via telephone circuits, and so they could send packets from one IMP to another, and each IMP could connect to a number of local computers, and that built out a whole network. Anyone on the network could directly address any other network by their ID. So their address was completely unique. Your address was made up of the ID of your IMP, followed by the ID of what port you are on the IMP. The IMPs would then have to figure out how to route a packet they were given to the correct IMP to send to the correct port. So all of the IMPs had to maintain a table in memory on their computer, because the IMP was a full-on computer. And so the IMP had a computer, and it had to maintain these large routing tables of how to get to any other node of the network. So if you said, I am at IMP number 6, I would like to send a packet to IMP number 9, it would have to figure out what hops to take to get there and send the packet on its way. So as packets came in, they would be stored by the IMP, it would analyze their destination, find the next hop to get to that route, and send it off. And if a link went up or down on the network, if we added more IMPs or something like that happened, all the IMPs would have to collaborate to figure out the new routing topology and the new routing tables. And this was quite a computationally intensive process, especially in the early 70s, and especially for the low-end computers that the IMPs were low-end computers the IMPs were built out of. So it took them a little while, and they had to work on the problem together. At around the same time, a completely different network was being set up in Hawaii. This was built out of radios instead of telephone lines, and being in Hawaii, they called it AlohaNet. And so AlohaNet was designed for much lower cost terminals. They were trying to share a very large mainframe with a number of other locations, and they wanted these other locations to just have a basic teletype and a little converter box and a UHF radio. And this computer box wasn't even programmable. It didn't have a computer inside. In fact, none of the terminals had a computer inside. They were just a teletype, maybe a smart CRT teletype, smart, and the only computer in the system was the head end, the big IBM mainframe. So storing routing tables on each of these No, that was not going to work for them. So they decided on a very different approach. Basically, in AlohaNet, if you want to send a message, you send it. Now, since wireless is a shared medium, it's very likely that two people will try to send a message at the same time. If this happens, both of their messages will be garbled and we'll lose them both. So, the main computer, every time it receives a message and decodes it correctly, it sends an acknowledgement back out. So, what the remote terminal does is it buffers that one message, sends it out. If it doesn't get an acknowledgement back, it sends it again. If it still doesn't get one back, it sends it again. And just keeps sending it. Each time it sends it, it waits a progressively longer amount of time to hopefully reduce the chance of collisions in the network. And over time, you can send messages at some rate that's like 15 or 20% of the total theoretical bandwidth, but you don't have to do any sort of scheduling or any complexity. It's very simple. So, when the engineers at Xerox PARC were designing the world's first personal desktop computer, and the world's first graphical user interface, and the world's first object-oriented programming language, and the world's first local area network, something they failed to commercialize. They failed to commercialize every single one of those technologies, by the way. Anyway, they needed a simpler solution than the complex IMP routing of wide area networks in ARPANET. So they looked to AlohaNet and developed Ethernet. The original concept with Ethernet was to use a big, thick coax cable. Big, chunky boy. And they called this guy the ether. So you run the ether around your network. All of your computers would tap into the ether and essentially treat it just like AlohaNet. Every time, except over a cable. So every time you want to send a frame, you send it. But they had another advantage here. Because these guys are on a cable instead of the airwaves, they could read back what they had just sent. And if the message was garbled when it came back, they knew that it must have had a collision. Two messages were sent at the same time. So now, because they could detect when a collision had occurred, they didn't have to wait for an acknowledgement. They could detect their collision, automatically wait some amount of backoff time, and try again. And this worked really well. So eventually, this technology would get turned into an IEEE working group 802, which might be a number you've heard of before, because it's going to come up a lot in this video, and that is historic Ethernet. Of course, Ethernet is a bit of a ship of Theseus. Modern Ethernet resembles it very little. Hopefully this history lesson makes you appreciate why some of the things are the way they are and why layer 2 is different from layer 3. So back to the modern world, I have some Ethernet frames to show you in Wireshark. Now note that I said frame here. So usually when we talk about TCP/IP stuff, we talk about packets, which are a layer 3 IP construct. But we're working on layer 2 Ethernet. So here we have a frame. So frames are made up of bytes or bits from the wire. So on the wire they're called symbols, which contain one or more bits of data. We piece those together into a frame, and then we have a whole frame of data which can contain a whole packet or sometimes part of a packet if the packet's fragmented. So for analyzing these kinds of things, Wireshark is an excellent tool, and I'm going to make use of it a lot in this video. So Wireshark. So here's a packet capture I did of a simple virtual machine, and you can see kind of a lot's going on. In this case, SSTP is kind of going wild. We're just going to start from the very beginning. So I'm going to open up this packet here, one of the first packets. You can see we have 90 bytes on the wire. So this is what actually was transmitted on the wire. It's this whole group here. And then within it we have a number of different things. We have Ethernet 2, Internet Protocol version 6, and Internet Control Message Protocol version 6. So this is our layer 2 MAC header, Ethernet 2. And then this would be our IP header layer 3 and layer 4. So we're just going to open the layer 2 header, Ethernet 2. Now there are actually two different Ethernet headers we have to be aware of. The first I'm showing here is Ethernet 2, which was developed by Xerox on their second version of Ethernet at 10 megabits. The IEEE developed a separate header called IEEE 802.3, which is the general Ethernet standard number. And the 802.3 header is much less frequently used, but we'll see it as well. So here, if we open this up, it shows us all the fields in the header, and we can click on them and see what bytes of the packet correspond to that. So you can see the first 14 bytes of the packet here correspond to the Ethernet 2 header. So first we have 6 bytes for the destination MAC address. So we lead with the destination. And in this case, it's identifying it as an IPv6 multicast MAC address. I'll get to that, what that means later. And then next we have the source MAC address, so where the frame came from. In this case, the OUI BC2411 belongs to Proxmox, and it's followed by A0, D0, C0. And the last 2 bytes we have are the type, or the ether type, which in this case is IP version 6 or 860D. In case you're curious, here's a table of common ether types. So IP version 4 uses 0800 and 0806 for ARP. 8100 is VLAN tags, which I'll talk about later in the video. 860D is IPv6. We also have things here like PPPoE, MPLS, LACP, and slow protocols, and a lot of other layer 2 protocols directly have their own ether type. So that's really all there is to it in Ethernet 2. We just have the destination is where the MAC address is going, the source, MAC address we came from, and type. So here is a different packet. In this case, this one uses the 802.3 framing instead of the Ethernet 2 framing, and it's really not very different. So we have destination MAC address again, we have the source MAC address again, and then instead of the ether type we have a length. And then padding will always be there whether or not it's an Ethernet 2 or an IEEE 802.3 frame. It's just this is a really short packet, so it needed some padding. So really, the only difference between Ethernet 2 and 802.3 is that for 802.3 we use those 2 bytes for the length. And the length can't be greater than 1522. For Ethernet 2, we use those 2 bytes to tell what protocol we have, and we figure out the length from the physical layer. Now, since most protocols use an ether type, most of the time we're going to see Ethernet 2 frames. But in this case, some logical link control stuff uses 802.3 instead, so we have a length. So the way you can reliably tell what type of frame you have is if the length field is greater than 1522, then it's Ethernet 2, and if it's 1522 or less, it's 802.3. So since the length field doesn't tell us what protocol we have, we need some other header to tell us what protocol we have in 802.3. And that header is called the logical link control header. So essentially the IEEE identifies what these bytes mean, so 42 means spanning tree. So we're going from spanning tree to spanning tree, and we have a couple other pretty much useless fields. But the logical link control header will tell us what the sub-protocol is if we're using an 802.3 frame instead of an Ethernet 2 frame. So I drew a picture here to help us understand how MAC frames travel on the network. So we have 3 people here. I know you're sick of hearing about Alice and Bob, so we're going to call them Zoe, Jane, and Kaylee. They each have a MAC address, and they're each connected to the big yellow ether. So now, let's take a look at how frames travel down this Ethernet line, how they're picked up by the NICs, and how they're ingested. So, Zoe wants to send a frame to Kaylee. So she fills out the to and from, and the ether type, which isn't relevant for us today. So once this frame is filled out, she transmits it onto the wire. So we use Ethernet encoding, goes on the wire, and it spreads out magically. So now, how does each of these 3 computers know what they should do with this frame when they receive it? Well, first for Zoe, it's easy. She just transmitted it. Her network card was just aware that it just transmitted this packet, so it can safely ignore it. If it would have needed the packet, the software would have done something else. So then it travels along the wire and hits Jane. So his network card is going to receive this signal, and since the to address doesn't match his, so he's got 000000 on the end, and this one doesn't have that address, his network card is going to ignore it. Then it'll continue traveling down the ether until it reaches Kaylee, and since the to address matches here, OABC, her network card is going to accept it and hand it off to the operating system. So by filtering these MAC addresses in hardware, and originally the MAC address was hardwired onto the Ethernet card, this greatly simplifies packet processing for the operating system. Because if you have a big LAN network with packets flying all over the place, your network card is going to filter packets that aren't destined for your address. And that means the operating system doesn't have to deal with a whole bunch of packets that aren't for it. But what if Zoe actually wanted to send it to Jane and Kaylee? Well, then she needs to send a multicast packet that's for multiple destinations. So there are some special values of MAC addresses that identify multicast frames. So in particular, if this byte here is odd, or it starts with a 1 bit, then it's a multicast. So if we flip that 2 into a 3, this least significant bit of this byte now means a multicast frame. Since we've dedicated an entire bit of the 48-bit MAC address to identifying multicast frames, this means hardware can just check that 1 bit to see if it's multicast, and it could be received by more than one client. It also means that half of our valid 48-bit MAC addresses are multicast. Fun fact. Now there's actually a number of ways of calculating this MAC address based on the higher level address, such as the IPv6 address. So I'm going to use 3333 and then the rest of it, which means it's an IPv6 packet. But just know that this least significant bit here has to be a 1, which means this one here has to be odd. So now Zoe sends the frame. Again, Zoe knows she just transmitted it, so she knows it's not for her. It goes down the ether, and Jane's network card and Kaylee's network card both have to decide what to do with this frame. So historically, simple network cards would just accept all multicast packets and make it the operating system's problem to deal with them. And that's a simple approach we can take. Modern network cards, though, have large hash tables of multicast addresses, and the operating system can program in which specific multicast addresses they want. Now, there's also a special multicast address that's all Fs. So notice that this is odd, so it's a valid multicast address, but it's also all ones. And this is called the broadcast address. So this broadcast address is a valid multicast address with all bits set, so it's FF. And so some higher level protocols treat broadcast differently from multicast. Wi-Fi, for example, has complicated ways of dealing with multicast and broadcast. But in general, if a device is unaware of multicast functionality, it should treat all multicast frames as broadcast frames and send them out to everyone. If a network card is unaware of multicast functionality, it should again treat everything with that multicast bit set as broadcast and accept it, let the operating system deal with it. Most protocols now are going to have a multicast address called a group address that they use and rely on. So in IPv6, there's quite a few number of these that are used by IPv6 protocols, and they allow the network cards to be specific in which frames they want to accept, whereas with using broadcast, you're just sending it out to everyone. Everyone has to deal with it. There's also a specific multicast group that is 0180C2, and that is used by Ethernet link layer itself. So when we talk about spanning tree and things like that, it'll come up again because that's multicast as well. So at this point you might be thinking, what does this crusty old link layer stuff have to do with modern IP networking? And the answer is very simple: neighbor discovery. In short, in an internet protocol network, either v4 or v6, we have an address. The address is on a subnet identified by a subnet mask. Maybe you've heard of this before. In many operating systems, it's represented by the number of bits of the subnet, but sometimes, like in Windows, it'll identify it like 255 to 255 to 255.0, which is kind of the old school way of doing it. So essentially what that subnet mask tells the higher level IP layer is that any device on that subnet is directly accessible on the link layer, and any device out of that subnet is not. That means when sending an IP packet, the IP layer has to do something very different depending on the link layer adjacency of our neighbor. Let's take a look at a packet capture to explain better what I mean. So looking at my IP addresses, I have an interface called ETH0, and on ETH0 I have an IP address 172.27.14.255/20. So 20 in this case is my subnet mask. Refresher on legacy IP subnets. A 20-bit subnet has this range to it, from 172.27.0.0 to 172.27.15.255. So we are roughly near the end of that subnet. Also in IPv6, we have this address with subnet mask of 64, so that puts the first half as our prefix and the second half as our host address within the subnet. v4 is easier. Subnets are always a 64. That's always right in the middle, halfway. So take a look at what happens if I ping a device within the same subnet as me. So I got the same prefix here, and I'm going to a specific address on that subnet. So ping works, obviously. Now let's take a look in Wireshark. So in Wireshark, here's the 4 packets that are significant. So we wanted to talk to : 70, but we don't know their MAC address, so we send out this packet here. So we have an Ethernet 2 frame. We're addressing it to IPv6 multicast, and it comes from our local MAC address, and its type is IPv6, 86DD. And then in IPv6, we scroll down a bit. So we're sending it from our own IPv6 address to an FFO2, which is a multicast address. and it's called a neighbor solicitation. So we're asking, who the heck has this address, : 70? Please tell us. And we're asking it on multicast. So any node that's on this network should see this link layer multicast and respond with their IP layer address. And that's followed up right away by this frame. So again, it's an Ethernet 2 frame. It's sent to my address, and it's from a Mellanox NIC, and again, it's IPv6. So what it says here is the target address was : 70, and that's associated with a link layer address of B8, CE, F6, blah, 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 for Mellanox. So we wanted to send an IP packet, but we know the destination is within our subnet mask. And within our subnet mask means they're on the same Ethernet segment as us. They share the same ether. And so we're not going through a router, we're going locally, but we have to figure out what their MAC address is. So we send out this neighbor solicitation, and we say, hey, I'm looking for : 70, please tell me. And everyone who's listening for those multicast frames receives that and says, oh, hey, I'm 70, and they respond back. That's a neighbor advertisement, or NA. So now we've figured out what the MAC address is on the link layer, and now from now on, we can replace : 70 with the correct MAC address, because we know what it is. So once we've done that, we follow that up with a ping request. So again, Ethernet 2 frame. Now we're going directly. So it's to the : 70's MAC address, which remember was Mellanox, and it's from my MAC address. And if we look here, it includes both of our IPv6 addresses. But we needed to figure out what the MAC address was first before we could use the IPv6 addresses. So coming back over here, what if I ping someone far away? So this, for example, is a public DNS server. So it's out on the internet. So I ping that. And again, the ping works, but let's take a look at Wireshark. So this is my ping out to the internet here. And you can say my destination is 2620 FEFE. But we didn't do a neighbor discovery, and we just sent this right out to this EAC automation. So who's that? So it turns out that EAC automation is actually the MAC address of my router. So if you've ever seen a network config where it says default gateway, what that means is if the IP address we're trying to reach is not within our subnet, then we need to find someone who can route our packet for us. It's too complicated for us. And so we use the default gateway. And in this case, the default gateway was : 1, and I already had the MAC address cached because it's talked to it before. So I sent a ping out to the internet. It sends the destination IP address as the internet address, but it sends the destination MAC address as the MAC address of the default gateway. So that default gateway is really only used to do neighbor discovery to look up the MAC address of the router. It's not actually used as the destination of any IP packets, because the destination is the internet address. Of course, it works similarly in IPv4. So this is again within my /20 subnet. So legacy is similar, except in this case we have two different protocols, ARP and ICMP. And ARP uses broadcast, so it can't be filtered as well. So this is called a who has. So who has.1.70 tell.14.0255. And so this is again protocol 0806. So it's not IP, it's ARP, which is distinctly different. And so we're saying our source MAC address is our MAC address, and our target MAC address is unknown. We don't know what it is. And then they respond, and they fill in their own MAC address and send us our packet back. So again, this is 0806, not 0800, so it's a different layer 3 protocol. And then of course we can ping. So if you've wondered what the subnet mask and default gateway do, and why you can only have one default gateway on most systems, and why the subnet mask is critical to get right, this is why. It's used for finding hosts on the local area network on the same layer 2 Ethernet as us, layer 2 segment. So that is neighbor discovery in a nutshell. So I know I've been talking for like 20 minutes now about the shared medium, the ether, all sending our packets onto the wire. And in reality, it hasn't actually worked that way since like 2003. But essentially for software reasons and because it works really well, we still kind of pretend it does. But why doesn't the shared medium Ethernet work well? Well, let's see what my more complex local network looks like. So over here, we've got 6 people. So we got Zoe, Jane, Kaylee, Simon, River, and Inara. So Kaylee is our file server. She has files. People access her files. Inara is good at talking to people, so she is our router. She's connected out to the internet. And we're just sending frames across, having our merry day. So frames are going down to Kaylee and from Kaylee to all the different clients. And some of them are going to the gateway at Inara, and they're just, this wire is shared. So we can essentially only have one frame on the wire at a time, because otherwise we have a collision. So we're limited in total to 10 megabits on traditional Ethernet. And that's shared between everyone, sending packets everywhere. So it's not great. So our solution to the shared media problem was bridging. Bridging multiple segments of the ether into one. So this shared ether is called the collision domain, because on this wire we can have two frames that collide on the same time. So what if we shrink this wire to be half as big? Now we have a smaller ether, and then we make another one. We bring it over here. So in the middle here I've got a bridge. So this bridge is going to receive frames from the ether on one side and decide if it should transmit them out on the other side. But by buffering this frame a little bit, it prevents a collision on this half from spreading to the other half. So we can have a frame floating around over here, and then it'll get ingested by the bridge. The bridge will decide what to do, and at the same time, another frame can be floating around on this segment of the ether. So now we've split ourselves up into two separate collision domains. So how does this bridge work? So imagine I'm a bridge connecting two different ethers, and I get a frame in. I'm just going to use short numbers because the text is too big. So my frame is from 02 and it's going to 04. So I have no idea where the MAC address 04 is, but I know that if it was on this right side here, someone already would have received it. So I'm going to send it off, or queue it to send it off on the left side. So then I'm going to go to my bridge forwarding table and I say, I just saw a frame that came from MAC address 2. So I know they must have been on the right side where my frame came from. So now I've identified that MAC address 2 is on the right side. I'm still not sure where 4 is. It could have been on the right or it could have been on the left. But we'll send the frame off anyway. Now I get a frame back on the left side and it's reversed. So it's from 02 to 04. So now I can add MAC 04 to the forwarding table as well. So I know MAC 04 is on the left. And I already know where 02 is. I know it's on the right. So I send it off on the right. So they keep talking. We get another frame in. This one is 204 and from 02. And this way, I know from my forwarding table that 04 is on the left. So I know I have to forward it to the left. So now I get a frame in that says 202 from 06. So I look at my forwarding table and I say MAC address 2 is on the right. That means there's no reason to forward this frame to the left because I already know that 02 is on the right, so they already must have received it. And as a bonus, an 06 is on the right now too. So the bridge continuously builds this forwarding table as it sees frames traverse back and forth on the bridge. And it knows where frames came in from, and it learns where those MAC addresses are. So now we can extend this a bit. I added a third port here on the bottom. So we already have our bridge forwarding table. We know where 2, 4, and 6 are. And now we get a frame to 8 from 6. And it goes to 8. And our forwarding table doesn't know where 8 is. So should we send it to left or should we send it down? And the answer is, if we don't know, we do what's called flooding. So we send it to both. So we send it to both down and left. And hopefully eventually we get a frame back from 8. So we can add it to our forwarding table. So you might have heard this referred to as flood and learn. So basically what happens with a bridge is it receives a frame. It has a destination and a source. It adds that source to its forwarding table. So in the future, it knows where to send frames to that source address. But at this point, it doesn't know where the destination is. So it sends it out to all of the other ports. Now next time it gets a response back from that MAC address, it can add it to its forwarding table. And in the future, it'll know which port it needs to send it out on so it doesn't waste bandwidth on the entire network, all of the collision domains. So now I get a frame in that says 3.3. So this means, because it's odd, we know that this is a multicast frame. And so that means we don't add it to the forwarding table. We just send it out to either everyone, or if we know who wants this multicast group, we can send it out just to them. So most switches at this point, especially switches that are unmanaged, will treat all multicast as broadcast. So if they receive a multicast frame, they will send it out to every other port. So multicast traffic, if you have a 24-port switch, it'll go out all 24 ports. Now more advanced switches can listen to messages that tell the switch who wants to listen to a multicast address. Then they can have their own multicast forwarding table that says which ports are members of multicast groups and should receive those multicast frames. But that's a bit more complicated. So at this point in history now, we've invented bridging. We can take two Ethernet networks and bridge them together, or more than two. So now we've shrunk the size of the collision domain, how many nodes we have on a single wire competing for bandwidth on a single Ethernet. But what we haven't shrunk is another important term, the broadcast domain. So essentially the broadcast domain is the size or number of nodes at which a broadcast will travel to. So a layer 2 Ethernet broadcast, if any node sends it out, how many other nodes will be affected by this? So the larger the broadcast domain, the greater chance you have layer 2 broadcast or multicast style problems. So a layer 2 Ethernet bridge is still not a particularly smart device. So it has the bridge forwarding table, it's only forwarding packets to destinations it needs to, but unlike a layer 3 router, which has things like time to live and loop prevention and equal cost multipath and things like that, bridges don't have any of these features. So if you make a mistake in bridging, you can end up where broadcast packets will flood the network and it's a bad day for everyone. Another possibility that some networks have a problem with is you just have too many clients on the same broadcast domain. So a lot of packets aren't broadcast, but some packets are. So ARP is broadcasty, DHCP is broadcasty, and their equivalents in IPv6, neighbor discovery and router discovery, they both use multicast, but again, bridges, a lot of bridges treat multicast as broadcast. So the enhanced filtering ability of using multicast in IPv6 isn't necessarily an advantage unless you have higher end switches. But anyway, imagine you have a network with, say, 10,000 Wi-Fi users. If you put them all on the same network, that might seem like a good idea, but now you have 10,000 DHCP queries, 10,000 ARP requests. You got a lot of shit going on, and that's just going to completely drown out the bandwidth you have in the network. I'm not even talking Wi-Fi either, that's a whole other nightmare. So now let's look at how this simple business network that I've set up in the past chapter might expand over time. So we used to have one ether, then we had two ethers, and then we got a 3-port bridge, so a NARA could connect directly in the middle, and that way the traffic going out to the internet didn't have to get straddled. So what if we eventually take this to its final conclusion where it's all bridged? Okay, this is what I got. So instead of having a shared medium, we now use full duplex Ethernet, and we use switches everywhere. So these 3 computers have a switch, these 2 computers have a switch, we have a switch in the middle, we have an NARA with the internet. Oh, by the way, Ethernet eventually completely got rid of that whole collision domain thing, so it's basically gone now. Gigabit Ethernet doesn't support it anymore. We just do full duplex, point-to-point Ethernet between 2 devices. Those could be a network card, could be a switch, but point-to-point. The whole broadcast domain thing, that's still a thing though, and we still have to worry about it. And there's one other thing we might have to worry about. So if I draw this a bit more structured here, like kind of like a tree. What if someone's like, well, we've got some bandwidth going to Kaylee the file server from River and Simon, and it has to go up via this link, through this switch, down via this link, to that switch, up to Kaylee. What if we just like shortcut this right here and make a triangle? Does that sound like a bad idea or a good idea? Well, you're in luck because I did some simulation today to figure this out. So I'm going to pop up Wireshark on one of these intermediate links, and we're going to ping from one system to another. Here's Wireshark, not much is going on. And start a ping, so we can see about every second we're getting a ping there. Nice. So now I'm going to add in that extra link here between the switches for redundancy, right? Oh God, what have I done? 40,000, 20 seconds, what the hell is this? Did my ping still make it? No, not really. They're kind of broken. So what I just did is I created a loop. In a layer 2 bridged Ethernet network, anytime we make a loop, the bridges aren't smart enough to save themselves. So in layer 3 internet protocol, we have limits on how much a packet can be forwarded. But in layer 2, we're pretending that we have this single wire ether, and so we don't have any of those limits because they weren't designed in the Ethernet 2 frame. So now, if someone manages to accidentally make a loop where packets can flow in a circle, then packets will flow in a circle. And they'll continue to flow a circle until they exceed the bandwidth of the links they're running on, which can basically lock up an entire network. Oh, it gets worse too, because when you have a loop, random packets will end up circulating around this loop, and they might end up in one way or the other way or whatever. They're flowing through the loop, and it messes up all the bridge forwarding tables too. So switches have no idea who's on what port because their loopback packets keep getting sent back around and they come in on the wrong port, and it's just a disaster for everyone. And in fact, when Ethernet bridging was invented in the mid-80s, this was a big challenge they had to solve, was how do they prevent a stupid engineer that plugs a cable in the wrong way from taking down a whole network. So this problem was eventually solved by an engineer at DEC named Radia Perlman, and she invented the spanning tree protocol. She also invented another protocol you might have heard of, ISIS. There's a dash in between there, don't forget that dash. So, how does spanning tree save us? So essentially, spanning tree implements the simplest form of a routing protocol. So in most higher level routing protocols, we have some sort of table that routes us on how we can get to all of our destinations or groups of destinations. But in spanning tree, we only have one destination, and that is the root bridge. So now every bridge in the network is exchanging spanning tree BPDUs across all of its ports. So now they have individual packets flowing between every bridge. They can share little bits of information. Every bridge also has an ID, or a priority. This can be set manually, but a lot of people leave them at the default, which is hex 80,000 or 32,768. So every bridge is trying to find the lowest cost route to that root switch. Whatever switch the network decides is the root, they're trying to find the least cost path there. So if you don't set your root switch properly, if you don't set your switch priorities, you may end up with a weird topology. So here's the setup we got. All of them have their default X 80,000 or 32,768. And so which one of these do you think should be the root? And I guess that's debatable because this path, or this path could be turned off. Spanning tree is going to turn off one of these three paths. So if you're an engineer and you say most of my traffic is flowing out to the internet, then you probably want this to be the root, because from the internet it's either going to go this way or it's going to go that way. On the flip side, if most of your traffic is going to the file server, Kaylee, you might want this one to be disabled. So traffic from the internet would bounce across this switch, that switch, and down. And it's not going to take this path because this is disabled to break the loop. But file server access would all go direct this way or coming in off the internet that way. And so you have to figure out which one of these you want to be the root and set that to a lower number. Now, if they all have the same number, then they use their MAC address. And the nice thing about MAC addresses is they're defined by the manufacturer. So you're pretty much guaranteed they're going to be unique. That means the switches are going to pick essentially a random switch to act as their master. So for the purpose of this, I'm going to set this guy to 70,000. So that means this link will become inactive. So I'll shade that purple. So this link will be inactive. These two will be active. And let's see how that works out. So here's what a spanning tree frame looks like. So it's an 802.3 frame. It has logical link control, subheader, and we have spanning tree. And this is not that big of a packet. There's very little information here. So what it says is that it's the spanning tree protocol in version 2, so rapid spanning tree. Usually we use rapid spanning tree. This particular port is a designated port, so it's not disabled. It says the root bridge has 28,672, which is hex 70,000. Our bridge, so the one we're talking to, is hex 80. So this means is that this particular bridge that sent this frame knows of some other route somewhere that has this priority, but its priority is actually higher. So that means that we shouldn't take this path if we find a direct path to that route. And so by sharing what the lowest route we find is, we can end up making a path back and identify what that is. And we say our bridge cost is 10. There's a formula for calculating cost based on bandwidth, but it's kind of dated, so high-speed links all end up being 1 anyway. You kind of shouldn't rely on it. But yeah, so in theory, slower speed links should be disabled first, but so this guy is going to send frames saying, I am 70,000. These guys are going to receive it, and they're going to say, hey, I'm 80,000, and they're going to send it back. So he's going to see that he is the lowest number because no one else has a number lower than him. Remember, they're only sending their lowest number. They're not sending the whole routing table. And then these guys on this link are going to see a frame that says, I am 80,000, but I saw a 70,000. So this guy says, my cost is 0. He sends that out to the 80,000. This guy says, you know, I have a route at gigabit, so I have a cost of, say, 10. Then he's going to send that out to everyone else, because this is his path to the root port. This is the path with the lowest root cost. So he sends this over here. So meanwhile, we've also got a cost 0 coming this way. So with a cost 0 on this port, cost 10 on that port, this guy says, you know, I should take the lowest cost link, which means I should probably disable this one. So if, for example, this wire didn't exist, then this guy would not have a cost 0 route or a cost 10. So he would not be saying, I have a cost 10. He would be saying, I have nothing. I don't know what I got. So this link would not get disabled and would come back up. So hopefully that basic explanation of spanning tree makes sense to you. It's not a technology that you generally want to rely on for a lot of things. So it'll help you if you accidentally miswire something. If you connect switches in the wrong way, spanning tree will quickly, well, not that quickly, but eventually it will disable those links. Your network will be a little bit broken, but it won't be like completely shut down. But, as I'll get to probably in later videos in this series, there's better ways to deal with large topologies like this at the IP routing layer. But at the link layer, be very aware of these loops. The loops have to be broken. If spanning tree breaks them, the paths on your network that you think traffic might be flowing over, it might not be flowing over. So now our network has functional spanning tree. Now there's only one path from any given MAC address to any other MAC address on the same broadcast domain. That means we can't have any loops because spanning tree disabled ports to break the loops. But what if we want to have extra links in our network for redundancy or more bandwidth? How do we do that? Now there's a couple ways we can look at this. So here's what we have already. These two links are active. Spanning tree is disabling this one. We could say this is for redundancy and leave it in anyway. But in this case, if this link were to break, then this link would become active via spanning tree. So we're saved from failure of that one wire. So now we have doubled up the links here. And what we want to happen is we want frames to take either one of them. So we have more bandwidth between these two switches here. But what spanning tree is going to do is it's going to pick one of these to disable. And it's going to pick one of those to disable. By the way, spanning tree breaks ties based on port MAC address or port number. So if you connect two ports to two ports, the lowest numbered port will be the one it connects. So of our 5 links here for redundancy, we're only using 2 of them normally. So how can we get some of these guys back up in use and working for us? So the protocol we're going to use to do this is called LACP, Link Aggregation Control Protocol. LACP was originally IEEE 802.3AD, and now it is 802.1AX. Those letters can be confusing because they duplicate letters across the different number standards. Now using 802.1AX or 802.3AD comes with some very specific requirements. All of the ports in a link aggregation group must be running at the same speed and the same duplex. So if we want to have, say, a 10 gigabit link with a 1 gigabit failover, we probably should rely on spanning tree for that. And spanning tree should be disabling the slower link, hopefully if it's configured right. But if we had, say, 2 10 gig links or 2 1 gig links, we could bond those with link aggregation. So here's what I got for a LACP setup. So our frame comes in, we're using the MAC address 0180C2 again, and it's called slow protocols. You'll find this term used a lot for Ethernet slow protocols. So Ethernet slow protocols are protocols that are used to manage the link layer essentially. Spanning tree probably would have been considered a slow protocol if the term slow protocols existed back then. But a bunch of these link layer protocols you'll see grouped under the slow protocols MAC address. So then slow protocols, it's an LACP, and we have the LACPDU. So we have an actor, which is the MAC address of one side, and the partner, which is the MAC address of the other. So he hasn't discovered his partner yet. So he just put in 0. So now in this frame, this actor found his partner. So these two MAC addresses are physically plugged into each other. And then there'll be another set of LACPDUs on the other link, and they'll be happy. So I don't really like to show like program-specific or brand-specific examples, but in this case, I don't think there's really a much better way. The LAC PDUs and Wireshark aren't very descriptive, so we're going to look at MikroTik Winbox because that's what I'm using in this test. So here's my bond config. So there's 2 ports in the bond, so Ether 7 and Ether 8, and they're in H.3 AD mode, so we're doing full LACP, we're not doing some non-standard stuff. So we're using ME monitoring. In Ethernet terms, the ME is the Media Independent Interface, and that's the interface between the Ethernet MAC and the Ethernet PHY. So the Ethernet PHY is what actually does the voltages on the wire. The Ethernet MAC is what does link layer stuff. The interface between those two is called ME. And so what ME detection means is when the PHY loses a signal. So it has a carrier that it knows that the other side of the Ethernet's connected. When it loses that carrier, then the ME monitor trips, and we know we lost that port. And hash policy. So hash policy is very important for LACP. So in this case, we can do layer 2, 2 and 3, or 3 and 4. So one danger we have in aggregating links is that it's theoretically possible that one of them could be faster than the other. And it doesn't have to be by much to cause problems. So at the higher level, if packets arrive out of order, that can cause really big problems because TCP will see out of order packets as a bandwidth limit, and it'll start reducing its bandwidth to try to reduce these out of orders. So a lot of care goes in when we do spreading the load across multiple ports, that we always try to send one session of traffic on one port. So what we're going to do in this case with a layer 2 hash is we're going to take the source MAC address and the destination MAC address and hash them. That'll give us a long number, and we'll just take one bit of that number, and if it's a 1 we go down one side, 0 we go down the other. So that's how we pick our 2 paths. So a given set of traffic will always have the same source and destination MAC, so it'll always end up going down the same path. What this means is on a large network, these numbers are effectively random, and so the traffic will effectively be statistically distributed randomly across both links. But in reality, a given traffic flow will always take the same link. So in general, if you have 802.3 AD, you should be using this for links between switches. These other modes are primarily useful for end devices. So say, for example, I have a Linux server. It has 10 gig and it has 1 gig. The Linux server is probably not going to participate in spanning tree because these are both 2 NICs. So then I could configure them as an active backup on the Linux side with no effort from the switch side. So Linux is basically going to pretend like the backup link doesn't exist. It's not going to deal with packets on that link. If the primary link fails, suddenly it's going to start sending packets out the backup link, and the switch is going to see that as a change in the MAC address. The switch will update its forwarding table, and suddenly the backup link will be used instead. That's the primary use case for these other bonding modes. But in general, if you're bonding between 2 switches, devices that support spanning tree, you generally want to be using the LACP mode. This mode will give you protection from miswiring. If you set it up wrong, you will end up with a horrible scenario where half your traffic gets dropped, for example. So that's what those other modes are. So following along the historical development of Ethernet, at this point we can reliably transmit large amounts of data through our layer 2 network by using bridges or switches. So by setting up a fully bridged network, we have point-to-point Ethernet between every device. We can send quite a lot of bandwidth across the network as a whole, as long as we don't exceed the bandwidth of any one link between the switches. But this great success of Ethernet means that now we have a bunch of other devices that all want to talk Ethernet, but we don't want to necessarily put them on the same broadcast domain as all of our other stuff. So here's an example. So these guys got a bit wild here. So they just had their computers for a while connected to the internet, but then they got a phone system that needed Ethernet as well. And maybe it doesn't rely on IP, or maybe it's proprietary or whatever, but it needs Ethernet too. So same layer 2. So we got some phones, we got a switch for the phones, we got a camera that we can look at from 2 different places, and we've just got a lot of extra wiring. So like this wire is going east-west, these 2 are also going there. Why can't we just put this guy like up on that switch, and put this guy like over on that switch? And it's because we want to keep these separate layer 2 broadcast domains separate. And in a lot of cases, keeping them separate makes a lot of sense. So if we have different purposes for the networks, we want to keep their communication isolated. So now I've redrawn the diagram a little bit based on how we could implement this with virtual LANs. So basically, I plug all the devices into their nearest switch, So this is on the blue network, that's on the orange network, that's on the green network. The purple network carries all the different colors at once, but they're tagged so we can separate them out. And then again, this switch has access to the different things. But again, every time we connect to an end device, we're stripping out the all tags, the purple, and we're splitting it out into its original network. Just for a little bit of terminology too, these ports on switches that connect to end devices that aren't using VLANs, those are called access ports usually. And the ports where we're sending our VLAN traffic between switches especially, usually we call those trunk ports. So see what it looks like on the wire. I'm sending some pings now. So if we take a look at one of these, you can see we have our usual Ethernet 2 frame. So we have our source and our destination MAC address. But now, for our ether type, we have a new field that is 802.1q virtual LAN 8100. So on the wire, these are still being transmitted by layer 2. We still have an Ethernet 2 frame, so we still have an ether type. But now we've added a different type instead. So instead of 0800 for IPv4 or 86DD for IPv6, we now have 8100 for virtual LAN. And taking a look inside our virtual LAN here, we don't have all that much to it. So we say priority is default, DEI is ineligible, and the ID is 69. So we're using the top 4 bits here as the priority and DEI field, and then we're using 12 bits for the ID. So 12 bits would mean we can go from 0 to hex FFF, that's 3 Fs, not 4. However, 0 is reserved for no VLAN tag, so that treats it as a priority only, and FFF is reserved for software use, and it should never be seen on the wire. So that gives us 4094 valid tags, from 1 to 4094. A lot of equipment also intermixes 1 and no tag, sometimes by default, sometimes unintentionally. So I wouldn't expect to use 1 and no tag interchangeably either. But other than that, you have 4094 tags to choose from. And then here is our real ether type, 86DD for IPv6. So by acting as the ether type field, we kind of added our own little shim in the header to fit these other little bits of data before the real payload. And then of course we have the IPv6 header and the ping. So now you might be saying, what happens to the bridge forwarding table? Remember, that's all the MAC addresses and what port they go out on? Yeah, that gets all kinds of messed up with VLANs. So in general, there are a number of different categories of devices and how they handle VLAN tags. Good switches, basically most switches that are managed or smart switches, will properly handle VLAN tags, and they will have a separate bridge forwarding table per VLAN. So essentially you can duplicate MAC addresses on different VLANs and it won't cause problems for the switch. Lower end switches, a lot of unmanaged switches, will pass the VLAN tags along and completely ignore them. So in this case, the VLAN tag just adds an extra 4 bytes to the size of the frame. The switch will read the first 2 fields, the MAC addresses, completely ignore the ether type and the VLAN tag, and pass it on as if it didn't exist. So this means we have one bridge forwarding table for all of the VLANs, and if we had the same MAC address on multiple VLANs, it could cause problems. And third, we have devices that are not VLAN aware and perform badly. So some unmanaged switches will drop VLAN tags. Some of them only drop it because the frame is too big. So if you reduce the MTU by 4 bytes, it'll work fine again. Wi-Fi also has its own header format, different from Ethernet 2, obviously, because it's over the air. So VLAN support in Wi-Fi is questionable. But anyway, assuming you have hardware that properly deals with VLANs, what are some parameters we have to configure here? So for VLANs, essentially we need to configure each port on the switch separately. So the first thing we need to configure is which VLAN we treat as native. So essentially, the native VLAN for a certain port is when a frame comes into the switch that does not have a VLAN tag, should we add one? And on that same VLAN, if a frame comes out of the switch with that VLAN tag, should we strip the tag and send it as an un-VLAN frame? So this would be the native VLAN for a specific port. A lot of software calls it the PVID or port VLAN ID. Now the next thing we need is which other VLANs are allowed to traverse this port. So depending on what sort of filtering abilities your switch has, it's very common to be able to select which VLANs can ingress and egress on a specific port. So this would be separately from the PVID. Almost always when you set the PVID, that particular VLAN ID is automatically enabled on that port. But you can add additional ones too. So if, for example, I have a server that needs to access 2 different VLANs, I could give it access to both of those. What about a port like this? So this goes between 2 switches, and we need to carry a number of different traffics. So in this case, I'm going to set the PVID to 1, and then we're going to say tag VIDs, and I don't know, we'll pick this guy, and this guy. So we'll say tag VIDs. So this guy sends a frame with no tag up to the switch. So how does the switch treat this? So switch just added a blue tag on the end of it, and now it looks in the blue forwarding database and decides it needs to go out this purple port. So it looks at the forwarding rules for the purple port and says, ah yes, blue is allowed, we can send it. So it sends it out here to this guy. Now this guy has a more complicated decision to make because there are 2 destinations for this frame, for example. It's going to be this guy and this guy. So depending on if this is a multicast or unicast frame, he might need to strip the tag and send it here, or he might need to keep the tag and send it on the purple link. So we'll say, for example, that he's sending it down the purple link. So he again looks at his forwarding table, sends it out again. So now this guy is encountering this frame. So this frame needs to go out egress on this port. But that port has a PVID that's also blue. So he needs to strip out that blue tag. So now that he's stripped out the blue tag, he can send it down the wire without its tag. Now it's, again, I cannot overstate this enough. These are layer 2 constructs. We're taking our layer 2 bridged network and pretending like we have 4094 copies of it on each switch. Again, this is not an IP layer construct. If your devices are on different subnets, the switches aren't aware of that. The switches don't do IP. They just do MAC addresses. And if you want to mix and merge things from one VLAN to another, it has to go through a device that's smart enough to do that, like a router. Switches aren't going to do that. I mean, layer 3 switches are routers, but unless your switch is also a router and is also configured as a router, it's not going to be sending packets between VLANs. So just to drive this point home, let's say this computer wants to access a resource on this camera. Now these are on different VLANs, so the traffic is not normally just going to flow between it. So if she sends out a frame on her orange VLAN, the switch is going to get it, and it's not going to know what to do with it because there's no destination on that same VLAN ID that matches where the frame is going. So probably they're going to send it off in a flood to all the other switches and devices that support VLANs. Now if you want to connect to, say we give this guy an IP address. So just to drive this home, blue and orange are different VLANs. Now our router, which speaks all the VLANs, has decided that orange is going to be FCO2 subnet at layer 3, and blue is going to be FCO1 subnet at layer 3. So if this guy wants to send an IP packet, so now we have an IP packet in an Ethernet frame, so it's going to send it out here to the switch. The switch has now added the orange VLAN tag, so we have IPv6, then we have our layer 2 frame, and we have the orange VLAN tag on that frame. So now we can send this whole bundle down to the router. The router can break these pieces apart, and then it can send out a new packet on the blue VLAN, back out, back down to that switch, and down to this device. So I think this is a big stumbling block for a lot of people when they work on VLANs. In a lot of systems that automate creation of VLANs, they really tie together this layer 3 IP addressing and the layer 2 VLAN addressing. And really these are fundamentally 2 different technologies that we often combine together. So just because you've created 2 separate networks, each of which is a separate VLAN, that does not mean that traffic is going to flow through the layer 2 switches directly to where it needs to go. Because they're on different layer 3 networks, the layer 2 switches can't handle that. They have to send it to a layer 3 router, which in most cases, most people have a single router in their house. And so all of your traffic that's going between VLANs is going up to that router and back down. Now, of course, because VLANs are layer 2 constructs, we don't have to just use them for subnets. We can use them for whatever we want. So one case, for example, might be, how do we handle an RO's internet connection? So all day we've been assuming we have orange devices, green devices, and blue devices, and then purple is a combination of all of that. We have a 4th connection here, and that's the internet. So what if we actually had our modem like over here? So physically it just made sense for us to put the modem over here. And we want to put the router maybe in a nice rack in the basement. Maybe this guy's out in the garage. So we'll connect him up to our switch. Now we got to give him a new VLAN color. What are we going to make him? We make him brown, yellow. What do you guys think? Yellow is easy to understand. So we're just plugging the modem in with a yellow. And then again, we still have purple coming up here. So now we've sent a packet out to the internet, so it's IP. It's encapsulated in a MAC frame, and now we've added the orange VLAN tag. So now we take this whole bundle and we send it off to the router. Now the router is going to route it and decide it needs to go out to the internet. So then it's going to give it a yellow VLAN tag. Maybe it also does network address translation if we're doing legacy stuff. So then it sends it out down the switches. The switches get here, and then this switch is going to strip that VLAN tag. So now with the VLAN tag stripped, it sends it out to the modem, and the modem has no idea that its MAC traffic and IP traffic were encapsulated on their journey to the router. So in this particular example, the upstream router, I guess you could call it, on the yellow VLAN is the modem, because that's where the internet is. But the VLANs don't care what direction the traffic is flowing, who's the DHCP server, whatever. All the VLANs care about is that each one of them is logically isolated from each other. And as long as all of the hardware and software you use treats that isolation correctly, it doesn't mess it up, this can work very well. So while it may seem like things down here at the link layer are much more primitive than the internet protocol and the network layer, we still have some security things we can do to secure our link layer. And the biggest one of those is access control lists, or ACLs. So you're probably familiar with stateful packet firewalls. This is the bread and butter of packet filtering today. Essentially, when a client sends a packet to a server, that creates a session in a state table in the firewall. So the firewall is going to keep track of the source of that session and the destination of that session. And when further packets go in either direction, they're going to get matched up with their session in the state table and allowed through. So if I make a TCP session, for example, to port 443, I'm coming from my IP address, I'm going to the server's IP address, I'm coming from my ephemeral source port, and I'm going to the server's port 443. So I send that packet out, the stateful firewall checks its rules to see if that is an allowed direction for the outgoing packet, and it adds a new connection entry. Now, when the server sends a packet back, it's going to reverse all those fields. So it's coming from the server's IP address from port 443 to my client to my ephemeral source port. But instead of having a separate set of firewall rules for packets coming back, we say, this packet belongs to a session that's already open, so we'll let it through. Because we really want to be concerned with who is making connections. We don't want to duplicate all of our rules to independently say, well, this connection plus the return packet. We don't want to have 2 copies of all the rules. And so that is primarily how firewalling works at layer 3 and 4, IP, TCP, UDP. Down at the MAC layer, though, things are much more primitive. So it is technically possible to write a stateful packet firewall at layer 2. But in general, when you're doing layer 2 packet filtering on the switches, remember these switches are much more simple bridging devices than routers. They're trying to do everything in a hardware switch chip as much as they can. So generally, we are doing a stateless firewall. That means the only thing we can look at are the contents of this frame. We can't match it up with other frames. So at a minimum, we have access to the source and destination MAC addresses, which could be multicast as well. Any VLAN tags the packet might have, so if the packet has a VLAN tag or doesn't, we have access to that. And what physical port of the physical switch the packet either came in on or is about to egress on, or both. So just with that, we can do some pretty powerful basic security filtering. But in most switches, they can go one layer higher. They can look at the IPv4 and IPv6 headers and compare on a couple fields in there. And some of them can also do layer 4 ports as well for TCP and UDP. But you get more and more limited in the higher level protocols unless your switches are more high-end. This is primarily used for things like DHCP guard and router advertisement guard. And let's see how that might work. So back to our favorite network. Inara is our router. And we have Kaylee, Zoe, and Jane, our clients. So Kaylee just joined the network, so she needs to figure out where the router is. So she's going to send a router solicitation. Now this is a multicast frame, and it uses that MAC address. This is like the IPv6 version of a DHCP request, except because IPv6 we use multicast instead of broadcast. So she sends this frame over to the switch. Now the switch could flood it out to everyone, or if it knows where this particular multicast address is, in this case it's called all routers, it would know it only needs to send it to the router. But we could also have a rule in our switch ACL table. So we could have a rule, for example, that says if the destination MAC is this router, so 02 is all routers, the only person who would ever need to receive a packet for 02 would be the router. So we could say only allow that to flow to port 1, so that everyone else doesn't see the router solicitation. So then we send that off to the router. So now the router is going to send a router advertisement back. So it's sending it from itself to her MAC address, and it goes here. But what if someone else is trying to hijack our network traffic and respond as a router? Now this would be, for example, like a rogue DHCP server, an IPv6, a rogue router advertisement or router. We could filter this at the MAC layer by restricting who can send these specific router advertisement frames. So in this case, it's pretty simple because no one's going to be sending to 33000002 unless they're looking for a router. So if we put this in, then no one else will know she's looking for a router. But they could still send an unsolicited router advertisement. So for example, we could write a rule like this that says if the ether type is 86DD, which is IPv6, and the next header is 58, which is ICMP, and the type is 134, which is a router advertisement, only allow that if it came in on port 1. So if anyone else tries to send a router advertisement, the switch will just drop it. Now, these sort of stateless ACLs are a bit tricky to get right because we don't have the reverse path, so we have to think about packets flowing in both directions. This can also be used to build out other things. So in this example, I'm filtering for router advertisements to prevent rogue routers. Another really common implementation is called like DHCP guard. So it prevents rogue DHCP servers in IPv4. And it essentially works the same way as this. It's looking for port 67, UDP port 67, similar though. And you can also use it to isolate clients from each other. So if you've ever seen like a guest network mode, they're essentially writing a rule that says traffic can either go to the router or from the router, but it has to be one of those two. So traffic can't go from client to client, it can only go from client to router or router to client. And that can all be done using these MAC level switch ACLs in higher end layer 2 switches. So in addition to switch ACLs at the link layer, another option we have for security is port level protection. So there's two protocols that are commonly used for this. 802.1x authentication to force clients to authenticate themselves before granting them access to the network, and MACsec encryption. So they each work a bit differently, so I'll explain them both here. Now again, this is a case where I'm not trying to talk about specific vendors or products, so I'm just going to show you what the encrypted MAC frames look like. So the first port-based solution I have is .1x. So I've got a switch here. It's got a router and two computers connected. It's got some extra ports. And we don't want these extra ports just hanging out enabled all the time. I don't know if you've ever taken your laptop and just plugged it into a random Ethernet port at places you visit. But if you magically connect to their internal network, they did something really terribly wrong for security. In general, it's a good practice not to leave extra ports around your building connected to your network. So some options you have are to either unplug the ports of the patch panel, which is very secure but requires you to manually go in there and repatch them every time you want to hook something up. You could turn off the ports on the switch if you have a policy of having one switch port for every physical drop. You can leave them connected and turn the port off on the switch. That's also a pretty good option. And the third option is to have the port disabled but let the switch turn it back on with 802.1x. So essentially force the computer to authenticate itself to the switch, then the switch will turn that port on. And the switch can also assign it to a different VLAN if it wants to. So Jane comes in to join the network. He plugs in his computer, and initially he has no access because first he has to authenticate to the switch. So the way Jane does this is via EPOL. EAP stands for Extensible Authentication Protocol on LAN, by the way. So he sends an EPOL frame directly on the link layer to the switch. So the switch then encapsulates his EPOL frame into a radius packet and sends it off to the radius server. The radio server comes out with a response, sends it back to the switch. At that point, the switch decapsulates the ePOL, sends it back on the link layer to him. And this exchange can go back and forth a few times until the radio server eventually sends an access grant to the switch, at which point the switch opens the port. Now, I've already talked about EAP authentication for Wi-Fi before. I have a video up here on that. And this works exactly the same way. It's the same protocol. So common methods are username and password using MS-CHAP or PEEP. And you can also do certificate-based authentication with EAP TLS. All of those are options. So taking a look at the wire here. So the client's going to try to log on. So spanning tree was doing its thing because that's also at the link layer. Then ePOL, we get a start message followed by request identity, response identity, and in this case it chose to use MS Authentication EAP, which is MS-CHAP. So this is, again, an Ethernet 2 frame. The type here is 888E, so that's the Ether type for 802.1x. And inside there's really very little, there's only 5 bytes. And in this case it's requesting an identity. And then its response, it has my name, that's the username in plain text, so it's not encrypted. If you use a PEEP or TLS, this is encrypted because they do an ephemeral key exchange first to establish a secure session. Then within that session, they exchange username and password or the certificate. For MS-CHAP, though, it takes many fewer messages, so it's quicker. On physical Ethernet, that's probably not a big deal, but on Wi-Fi, that can be a huge deal. And so essentially, we send the username in the clear. The radio server sends back a random number. We encrypt that random number using our password and send it back. Then the radio server can confirm that our password was right. And so now I can ping across. You'll see pings just fly around. So as you can see, I can see the pings going by. So this doesn't provide any encryption on the wire. It just provides authentication that the device that is plugged into a switch port has a user account on the network. And optionally, you can set a VLAN too. There's some additional information you can feed back from the radius database that can tell the switch things like to rate limit a port, what VLAN to put it on, things like that. Now, it's also not entirely secure, so it's possible, because this isn't encrypted, that someone could insert themselves on the wire, pass the ePOL frames through, and then once the real device authenticates, they could also use that connection of their own. So there's things you can do, for example, so that the switch can add a MAC filtering rule to its ACL table, so it only accepts whatever MAC address did the ePOL handshake. Then that one MAC address will work. Of course, you can do MAC address spoofing to get around that, but you're adding more and more layers of security here so that at least if someone comes in with a laptop and plugs it in your conference room, they're not on your internal network. Also, all of the security cameras that I have at my house, they support 802.1x, which is really cool because if you're worried about someone unplugging a camera above your door and plugging their laptop in, which would be kind of hard to do undetected, but if you're worried about that, you can set your cameras up to use .1x and set those switch ports to require .1x. And that way, if someone unplugs your camera and plugs their laptop in, they won't authenticate and it'll be more secure. So here's a case where you might want to encrypt all of the link layer traffic on the line. So in this example here, I've got the LAN set up again with all the usual friends, but we've got, say, 2 buildings. Maybe they're not that close together. Maybe we leased a line from the telephone company and we're running this fiber outdoors. And we're worried about some attacker snooping on this line here. So we want to encrypt everything when it leaves here and decrypt it again when it enters here. So we don't have to modify our network to use other encryption. So encrypting at the MAC layer might not always be the best option for you. Maybe it'd be better to encrypt at a higher level like TLS, but it's available if you want to use it. So the MACsec link is up, and you see we see ePOL and we see MACsec. We'll come back to ePOL later. But basically, if I take a look at one of these frames, it's got a basic Ethernet 2 frame, but it has a new Ether type, 88E5. Then it has a security tag, which doesn't have all that much to it, but it has the MAC addresses. And yeah, we're not going to be able to use the rest of this stuff. So next I'm going to start a ping. And I'm pinging, and you can see that these ping frames here are just showing up as MACsec frames. So inside this data is my ping, but I can't see it because it's been encrypted. And packet number and the ICV will help to decrypt it, but I don't know the key, so I can't decrypt it. Now, some higher end switches can do MACsec in hardware. This can make it very, very fast. So if you have high-speed links between buildings, for example, and you're concerned with people physically intercepting your fiber lines, I know this is a huge concern with data centers and unencrypted traffic between multiple data center buildings on the same campus, for example, or nearby data center campuses, especially if you're worried about the NSA. MACsec will certainly help you make sure everything that goes over the link is encrypted. Do I recommend it for home users, though? No, not really. It's probably not for your scale. So at this point in history, we've really peaked at the development of Layer 2 Ethernet bridging. Layer 2 segments got larger and larger and larger, using VLANs to isolate traffic for a few very expensive routers, and we ended up with very large layer topologies. However, we found this didn't scale quite so well as we'd hoped. Let's take a look at an example. So if you studied network engineering, this might look familiar to you. This is like the traditional 3-layer system. So we have access switches, which are connected to individual clients or servers. Those are connected up to their intermediate distribution switches. So in this case, each access switch has 2 links to 2 of the distribution switches. Then we have the distribution switches connected to all of the core switches, and those are finally connected to the big router connected to our big internet connection. In network engineering, we refer to traffic that goes up and down in this diagram as north-south. So I've got a little compass arrow here, so north is towards the internet, and south is towards the user, or the device. We also refer to traffic that moves device to device as east-west, because it flows sideways in our network. And the type of traffic you have is a big determining factor in whether you need to engineer for north-south or east-west links. For example, if you're a cloud-based company, you have nothing on-prem, you're just trying to get all of your computers to the internet, your traffic would be extremely north-south. And you would probably not care about east-west bandwidth problems. If you're more on-prem or you're running a data center, for example, east-west might be your bread and butter, and that might be very important to you. So anyway, all of these yellow links represent Layer 2 bridged Ethernet. So the orange switches, the pink switches, the purple switches, these are all Layer 2. This whole thing is one giant broadcast domain, aside from the VLANs. So if we were to say that this is our root port and spanning tree, then what links would we have to disable to get to the root port? So now spanning tree did its thing. It tried to find the shortest path to the root port and disable any extra links to prevent loops. And we ended up with these yellow links still active. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 links got disabled. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12 of them are still enabled. So we disabled more than half of our links to get traffic to not have a loop. So traffic is going to flow heavily through this switch here. In the north-south direction, we're overloading this switch and we're underloading this switch. This switch doesn't see a ton of traffic just from these end guys out here. And if we need to go east-west, then most of it's going to end up switching through this switch anyway. This switch is only aggregating 2 out of 3 of these guys, and it's just kind of a mess. Now in spanning tree, we do have the flexibility of adding additional cost to each port artificially, aside from just the bandwidth. So we could do that to try to balance the tree. So maybe I'll do that and see what that looks like. So now this one has 3, this one has 2, this one has 3. So there's more load balancing going on across these switches. So roughly a third of our traffic will take each of these links up to the root port and then up to the router. But this is still not very efficient. We're only utilizing like half of our installed capacity. And all of these other links are pretty much just for failover. So we can delete any switch from the topology, any link from the topology, and spanning tree will fix that, failing over, but we're not going to be using these effectively most of the time. So fundamentally, this is a problem that Layer 2 Ethernet has. It was designed as the single ether with everything transmitted on it. And as we've added bridging over the years, bridge forwarding, it's not really designed to route like Layer 3 is. If we want to make use of multiple paths, equal cost multipath, for example, we would probably want to make use of a Layer 3 topology, where everything is routed instead of bridged. But I guess back in the early 2000s, that wasn't so popular, so we started developing routed Layer 2, as weird as that sounds. So the basic idea with routed Layer 2 is that we treat MAC addresses as our routing address, and each of these switches shares their forwarding DB over ISIS. So now all these links can come back up due to spanning tree. And as we find where a MAC address is on the network, that switch will share it with other switches via ISIS, and they will add it to their forwarding DB. But they will treat each MAC address separately as a separate route. So they will find the most efficient path from one machine to another machine, even if that possibly means multiple paths. They'll take one of them at a given time. Now there were two different protocols that were developed to implement this. The first one was called TRILL. It was developed by Grady Perlman, the same woman who developed spanning tree and ISIS. So I guess it makes sense to put those two together into TRILL. Then the IEEE made a standardized and incompatible version they called shortest path bridging. And neither of these caught on. And I actually tried really hard to find an open source implementation for Linux to demo this, and I could not find a single one. So you're not getting a demo today. Now what I can show you is how you can replace this whole topology with layer 3 and get rid of these layer 2 problems. Either using a pure layer 3 network or using a layer 2 overlay technology called EVPN VXLAN. So now what I've done in our topology is I replaced our large broadcast domain with much smaller ones. So each of these red nodes down here are a layer 3 switch router combo. So they have a broadcast domain that spans just their attached devices. So maybe this is like a 48 port gigabit switch. I could have up to 48 devices. Maybe I have a couple of VLANs that are brought out to this particular switch. So in that case, I'll have a couple of layer 3 subnets. So I'll give this one, for example, so I'll give this red switch here a /60, so he can have up to 16 VLANs off of himself on those 48 ports. And then I'll do that to all the other ones. 10, 20, 30, 40, 50, 60, 70. Okay, so now the computers on this are no longer on the same broadcast domain. So for this computer here, he's going to have an address out of the 20 subnet, and this computer here is going to be out of the 10 subnet. So they're not going to be on link anymore. They're going to have to go to their router, which is the red guy. And then from here up, all of these green links are point-to-point Ethernet. So they're two Ethernet cards directly connected together. This is a router, this is a router, this is a router. And this guy up here is probably doing BGP to the internet. And the rest of these guys are probably doing OSPF, or I don't know, maybe if you're really into ISIS, you use ISIS instead. They're both pretty darn equivalent. So layer 3 routing protocols have a ton of flexibility, and that's why there were so many efforts to bring ISIS down into layer 2. So ISIS was uniquely skilled at this because it's based on DECnet, which runs directly over layer 2. So ISIS doesn't use IP addresses, it just uses MAC addresses, which I guess makes sense if you're doing link layer bridging. But when we do IP layer stuff, layer 3, it makes a lot more sense to use a protocol like OSPF-v3 for IPv6. If you really need to route IPv4 legacy stuff, then I guess you could use ISIS to do both, or just run OSPF-v2 and v3. So what we've done here, though, is fundamentally we broke up our large, very large broadcast domain into a whole bunch of small ones. So instead of trying to break people out into VLANs to shrink the broadcast domain, because each VLAN has its own broadcast space, essentially, we've given each switch in the rack its own address space. So now we have a 48 port access switch, we've got 48 computers connected. We can put them on different subnets, we can put them on the same subnet, we can put them each on their own subnet, and most of their traffic is no longer going to be going to an Ethernet address, it's going to be going to the router. So I mentioned earlier in this video how neighbor discovery works, how NDP and ARP, if you're on the same local subnet, you try to go on link using MAC addresses. If you're off link, then you have to go to your router. And so these switches are now acting as that router, acting as the default gateway. And then once we get traffic into layer 3, we can ping pong it around the network using traffic engineering, OSPF, tools like that. So what does the routing table of this router look like? So he's got 10 locally. If he wants to go to an address in the 30 space, which of these two Ethernet interfaces should he take? So we're going to go to 30 via. If he takes this link here, ETH1, he goes up to this router. That doesn't have a direct connection here, so he has to go up another layer. You could choose either one of these. So if he takes this path, Then you come back down here to this router, or you can come back down to the router we were already at. Bit of a convoluted path, but you could make it. If we take ETH2, we go up to this router and come straight down to 30. So ETH2 is probably a better path there. Then, for example, if we want to go to this guy here, 60, he's on router 1 and router 2, but not router 3. And we're on router 2 and 3, so 2 is common, so we probably should go via that one. In this case, it's ETH1. But what about this one here? So 20. So this is router 2 and this is router 3. We're also on router 2 and router 3. So it's the same if we take this link or this link. So we can just add both of them to our table. And that will mean that when packets come in, we do the hash just like we do for LACP, and we decide which of these two paths to send a packet down. Now, just like LACP earlier, we're going to do a hash of some part of the packet header to decide which link to take, but in this case, it will statistically load balance across both links if you have enough traffic. If you just have one flow of traffic, it won't, but that's because we want to keep one traffic flow on a given link at a given time. And so now, all of my east-west traffic is handled entirely by these three routers pretty efficiently. And if I were to disable any of them, we can kick it up to the next level routers to handle failover. And when we're going out to the internet, where our BGP routes come in, then all of that traffic gets aggregated here on all three of these routers. It gets handled by both of these routers, and it gets handled by this one backbone internet router. So this would be called like our edge router. And maybe if you have two internet providers, you would have two of these, doing BGP to each one separately, and then you can do quite a lot of failover up in the core level. So the one downside to a layer 3 network is that devices can't roam across the network like they used to be able to do. So in the old days of large layer 2 networks, if you moved your computer, or a virtual machine for example, from one port on a switch to another port on another switch, you would send out your frames as your new address. And relatively quickly, all of the bridges would update their forwarding table of where your MAC address is. That would happen due to flood and learn, which is fun. And it wouldn't take that long. So for example, if we have a bunch of access points, you move from one access point to another, you're now using a different bridge as your gateway, but all the other bridges in the network figure that out. If you have VMs, same thing. They move from one host to another. The bridge forwarding tables figure themselves out. Now, if you're into the fancy cloud-native Kubernetes lifestyle, they actually have a pretty simple solution for this, and that is the container takes its IP address from the host. So if you have a container farm, each host might get a /64, for example, and when you start up a pod on that host, you can take an IP out of that host space, the routers will route, all will be good. But when we do other stuff like wireless networking or legacy VMs, vMotion stuff, we need a way to migrate stuff across the network and have it think it was where it used to be and not straddle these layer 3 domains. And to do that, we use a technique called EVPN VXLAN. So in EVPN VXLAN, these guys get promoted from routers to VTEPs. So a VTEP is a VXLAN tunnel endpoint. And essentially what happens at a VTEP is we take these layer 2 link layer frames and we encapsulate them in UDP. So MAC in UDP in IP. So now each of these VTEPs acts like a bridge. It has a bridge forwarding table. And its forwarding table might not be another link. It might be the IP address of another VTEP. So if I move this computer somewhere over there, and I move his link with him over here, this bridge will now learn his MAC address because he moved as it used to with flood and learn. And then that will get sent out across the other VTEPs as either multicast or BGP, and the other VTEPs will learn on their bridge forwarding tables where this MAC address now is. Now because we encapsulated this packet in UDP and IP, we transit it over the IP network using all the good equal cost multipath stuff, but when it comes back out the other end, it's still a MAC frame, and we still pretend that it's in the same link layer space. And all the same pretend link layer stuff like the old wire ether, all that still applies. Now there's two ways to do this. There's Unicast or Multicast VXLAN. So in that case, each VTEP acts as its own forwarding table, and if it doesn't know where to forward something, it sends it out to all of the other VTEPs. If you have a small scenario, this works very well. So small clusters of a couple nodes, you're not duplicating that many packets. On the large scale, though, we use a technology called BGP EVPN, where the VTEPs share their MAC addresses they've learned over BGP. So now we bring in a BGP server. I don't know what color BGP is. So this is a route reflector. So each of these has a logical session with the route reflector to send their routes. And then we probably have 2 route reflectors for redundancy. And these are just regular servers chilling on the network. They can be anywhere. If I get my lines looking nice. And so now, when it discovers the MAC address of this computer that moved, it sends it to the route reflector, which reflects it back to all of the other VTEPs over BGP. And then this is BGP, so this is running on top of the layer 2 network. These aren't physical wires. These are TCP connections. So this guy can be part of one of these higher end switches, or it can just be hanging off on the network somewhere. And we just have 2 of them for redundancy. And of course, I have a video on my to-do list that I haven't started making yet on EVPN VXLAN in Proxmox. It's part of their SDN beta still, but I'm planning on taking a look at it eventually. So I hope you guys enjoyed my look at the history and evolution of the Ethernet link layer. I know I've touched on a lot of topics that probably could be a full-length video on their own, but I hope that this overview of them has given you enough information to go out and set up your networks in a more manageable and functional way. I was really hoping to dispel some of the myths surrounding VLANs in this video, and so I hope that's done that for you. I have a follow-up video coming up about the layer 3 counterparts, so routed networks, static and dynamic routing protocols, things like that. And considering how long this video took to make, that one will probably not be out for a little while. But I really hope you subscribe so you can see when it comes out. I don't have any sponsors for this video, so if you want to give me a tip or anything, I have a link down in my description to my Ko-fi, where you can give me donations if you think I've deserved it. If you want to follow me and chat with me about any of these topics, I have a Discord server, link is also down below, where we talk a lot about IPv6 networking, Proxmox virtualization, things like that. Pretty great topics, and I have a really great community there. So until next time, I'll see you guys on the next adventure.